Hi everybody, I'm going to talk about tosylates in this video. So tosylates are just another way to turn alcohol into a good leaving group, really. So we're just looking at these as an alternative to alkyl halides. So we've looked at a couple of reactions where you can have an alcohol and turn it into a bromine or a chlorine. This is another way of looking at that. It's just going to be a slightly different leaving group, but we're still turning that OH into a good leaving group. Okay. So first off, we need to talk about the structure of tosyl chloride. So TS is going to equal this sulfonyl substrate. Okay, where we have something attached here, and that attachment could be chlorine, it could be OH, it could be a variety of things depending on what you have right here. So TSCl is all of this stuff. With a Cl right here. Okay, so we're looking at adding this entire big group onto our alcohol. So what we're going to end up getting here is we're going to have the oxygen that's going to be bound to the sulfur. And all that other stuff is on there. Okay, this is also written OTS, it just in terms of a shorthand so that you don't have to draw this whole entire thing out every time. So when we're looking at this, there's a couple things that we want to think about. So notice how the stereochemistry is retained the whole time, right? I started with a wedge and I ended with a wedge. Okay, that tells us we don't actually have any kind of reaction happening at that stereocenter carbon. It's all happening from the oxygen. Okay, so we want to keep a couple things in mind here. So this reaction is going to work on primary, secondary, or tertiary alcohols. Okay, so unlike some of the other, thionyl and phosphorus tribromide, where we're limited in what kind of alcohols we can use any type of alcohol for this reaction, and it's going to retain the stereochemistry. Okay, so let's go ahead and take a look at the mechanism so we can see why we're getting retention of that stereochem. Okay, so our very first step here, we're going to have our oxygen lone pairs come and attack that delta plus sulfur. And this is going to look a lot like we saw in the thionyl chloride mechanism, where we have those electrons from the SO pi bond move up onto one of those oxygens. Okay, so we're already starting to see here how we're getting some of these bonds made. So if I just kind of scroll up real quick here. So we're looking to make the O sulfur bond. So we've actually made that bond. The only things that we need to get rid of now is we need to kick off the chlorine and we need to deal with that hydrogen. And then we're getting to our tosylate. So once I'm here, just like in the sulfonyl chloride mechanism, or thionyl chloride, goodness, we're going to reform that OS pi bond, and then our chlorine is going to act as a leaving group. And then I get to here, and I've got chloride on the side. So what we're going to have now is, as we go along, we also have pyridine here, which I should have put that in the beginning. Okay, just like with the thionyl-chloride mechanism, our pyridine here is just acting as a base once we get to this positively charged intermediate. Okay, so our nitrogen is going to be our basic atom. Go grab that proton. And we end up getting our final product as well as pyridinium chloride. Because that's where our Cl- is going to hang out. Okay, so I can understand why some of us would want to think that like this chlorine is going to be our new nucleophile, but because we've got this pyridine around and we've got, you know, at least one equivalent, if not more, of pyridine around in here, that pyridine is going to be soaking up the proton here, and it's also going to be kind of collecting that chloride to make it so that it's harder to use that as a nucleophile. Okay, so this product can be isolated and bottled. So I like to think about when you can bottle something, it's going to be fairly stable, like shelf stable. Okay, so it's not a reactive intermediate by any means. This is like a full product. So once you have that product, you can do a variety of things with it. So I mainly want us to be able to know that you can install a tosylate onto an OH and how it behaves as an alkyl, like essentially as an alkyl halide replacement. I'm not really going to be testing you on this particular mechanism in any way, but I just wanted you to be able to see what it looks like so that it's not super mysterious. It's definitely chemistry that's more second semester organic chemistry because it's more kind of carbonyl type chemistry, but it's still something that I think it's good for you to see it now just so that we can kind of get used to it. Okay, so the way that we can use these, we're going to treat tosylates just like alkyl halides. So if I take this tosylate that we just made, and let's say I want to do an SN2 reaction on it, then I throw in sodium cyanide. We're going to have the cyanide go and attack. That whole group is our new leaving group. And then I'm going to end up getting inversion because, again, this is an SN2 reaction that I'm doing. And then my leaving group here is going to be this great big monster of a leaving group. Okay, so we're ending up with this. So this is very, very stabilized. And because it's such a stable negative charge due to all of the resonance that's over here, you know, it's very similar to the resonance of sulfuric acid. It's a very stable negative charge, and it's a very good leaving group because of that. Okay, so we're going to think about these tosylates as just being the same as alkyl halides. Okay, they're going to do all the same reactions that an alkyl halide would. Alrighty, so as always, let me know if you have any questions, and I'll see you all later.